Okay, so hello everyone. Going to go through a review of Module 2 and specifically looking at the theory without all of the code that's involved in sort of putting this into application. Through discussions with a few of you guys, I can understand that the Python aspects that I've been trying to teach you guys have maybe become a little bit difficult, and in places that means that you're losing sight of the theory that we're trying to teach at the same time. So coding is a tremendously important aspect of being an aerospace engineer because it enables us to do calculations that we simply cannot do by hand. More often than not because they're too laborious. We have to do things over and over again. So it's a really important skill that you guys need to be able to work on, and specifically because this course is being taught asynchronously, I can give you examples that you have access to a computer to do. So if I was just giving you handwritten stuff, then you'd be able to code it up, and that would not be fair. That said, I'm going to go through some definitions and terms and a recap of the theory, including why we're applying different loads, such that you guys can hopefully see why we do the things in coding that we do, and then you're free to solve it however you want. You can do it by hand if you want to. I wouldn't know. You can do it in MATLAB if you want to. I'd rather you did it in Python, but that's fine. You can do it in MATLAB. Do it in Excel, do it in C, do it in Fortran, do it in Java, do it in whatever you want. But let's try and go through a recap of what all of these different concepts are. So we've been looking at, let's just remind ourselves what we can do with a statically determinate structure. So if we have a statically determinate structure, we have a degree of indeterminacy that's 0 or lower, and in general it will have 3 maximum external supports. So we can use a free body diagram, and let's say we can use a free body diagram to determine the reactions as a function of the external load. Say, for example, I've got the structure that we looked at. In the virtual work example, we had a structure that had a built-in and a roller support, and it had P2 and P1 on the structure, and we were then able to determine these 3 reactions. So we had RAX, RAY, and RCX. So the free body diagram allows us to determine these as a function of anything we apply. Okay, I could also apply other loads to the structure. I could have, say, P3, P4 here. I could have things coming off at different angles. P5, for example. I could have all these different loads, and because these are just numbers, I can, using the equilibrium equations that we have to have 0 total force in the x direction, the y direction, and 0 moments, we can determine these 3 things as a function of whatever we put on the structure. Okay, I'm just putting those on there for the moment. I'm going to get rid of them now. So then that's what the free body diagram enables us to do, as long as we've got just 3 reactions. We then had the method of joints, and again, method of joints is something from previous classes, so I'm hoping you guys are pretty good with it. So we then use the method of joints to determine all of the internal forces within the structure. and then more often than not, these internal forces will be a function of the reactions and the applied load. Okay, so let me copy this diagram down again. So once we know what P1 and P2, they're just numbers. Once we've done the method of joints, we'll have some numbers for these reactions. We can then solve for 1, 2, 3, 4, 5 internal forces. So we would end up with, let's choose a different color, F. And we normally say lowercase f 1 through 5, 5 internal forces. And I've just said it's a function of internal forces, a function of the loading, P1 and P2, and the reaction. So REX through RCX there. So there's also RAY included here. So this is just a bunch of equations. So again, free body diagram gives us, and let's write this down, we get the reactions, which for us would just be a vector. We'll say that's RAX, RAY, RCX. I'm just choosing to store these in an array and a vector. They're not relating to dimensions at a point. We would end up with reactions is a function, and we'll call it FBD of P1 and P2. Okay, so that enables us to get the reactions, and once we get down here, we can then use the reactions here, and we've got P1 and P2. We can get all of the internal forces of a structure. If you want to know the stress in any member, stress is just force divided by cross-sectional area. So we've got that, that's good. If we want to know how much each member gets longer or gets shorter, then we can just use the constitutive relationship. We get delta L is equal to the internal force multiplied by the length of the member divided by the Young's modulus divided by the cross-sectional area. So we can get all of these things now. Okay, this isn't anything new. This is stuff that you had coming into this course, how to solve using free body diagram and the method of joints. What we moved on to and where we introduced new things is we said, okay, what happens if we haven't got a roller support on the right hand side? What happens if we get rid of this roller? Or what happens if we never had one in the first place, for example, and we've simply got two built-in supports? Well, this will give us another reaction. Sorry, this should have been RCY there. I'm so bad at mixing up X and Y when I do things. Okay, so we've got 4 reactions now. Okay, 4 reactions. We've still only got 3 unknowns. Okay, sorry, 4 reactions. We've still only got 3 equations. Those 3 equations are sum of forces in the X direction equals 0, sum of forces in the Y direction equals 0, and the moments are equal to 0. So we can't solve for all of these. So we say one of these is a redundant reaction. And what we mean by that, it's redundant because the whole body can maintain static equilibrium with just 3 of them, as we've shown. It can maintain static equilibrium with 3 of them, so there's, you know, 1 too many reactions here than it really needs to have. So we call one of them redundant. So if we have 4 external reactions, then one is redundant. And the way that we solve for the value of the redundant force, we introduce the force method. Okay, and the fourth method, we can loosely describe as set the redundant to 0, see how much the structure moves in the direction, or see how much the structure moves in the direction of the positive redundant force. Set the reaction equal to -1, see how much the structure moves back, and then the ratio of those two amounts gives us what the value of the redundant force has to be. So let's write this down. 1. Set redundant equal to 0. Okay, so in that case where we set our redundant equal to 0, we've got, going back to this problem, P1 and P2, we've got RAX defined, RAY, RCY, and RCX is still here, but we've set this one equal to 0 now. Okay, so that's equivalent to putting a roller support here, but we're just going to say we'll set the reaction equal to 0. If the reaction is equal to 0, then this is not providing any horizontal equilibrium at this node. Okay, so we set this equal to 0, and what this leaves us with is 1, 2, 3 reactions to determine as a function of this applied loading. Okay, and we can do that because we've got the free body diagram where we have those 3 equations. So set the redundant equal to 0, and then what we're going to do is do a free body diagram to get the 3 remaining reactions. We're then going to do the method of joints to get the internal forces, and ultimately what we want to determine is, let's zoom in on this, the structure is going to move somewhat under that loading. Let's say it moves like this. And so that node will move some amount to the right. Okay, if we apply this loading, because we're pulling the structure to the right, this structure is going to move to the right. So we called this delta CX, which is the amount the structure moves in the direction positive CX. Okay, so we can determine that amount, and we're not going to think about how we actually determine that amount at the moment because I'm just talking about what the force method does. But in order to do that, we need to do a free body diagram and the method of joints, and then some sort of method to determine this displacement. Okay, because what we end up with is delta CX. Okay, so we've got that. That's how much the structure would move if the redundant reaction wasn't there, which is equivalent to setting equal to 0. Because this is a built-in support, in reality, what it means is that we know this displacement isn't 0. This displacement here is not, this displacement here is 0. This displacement isn't equal to this value. This is the value that this node would move to the right if the redundant reaction was set to 0. Okay? It follows that when the redundant reaction has its actual value that it must have to maintain static equilibrium, the displacement here would actually be 0. So the way that we solve for this is we say, okay, we're going to set the redundant reaction to be -1. And then we're going to see how much the structure would move in the other direction just because of that reaction of -1. We're going to ignore P1 and P2 for the moment. Let's go back to my dark green. We then set redundant is equal to -1. Okay? Haven't even introduced any virtual forces just yet. This is just part of the force method. Okay? No work energy. This is just how we do the force method. We set the redundant equal to -1. We're going to have to do free body diagram. We're going to have to do method of joints, and we then get the second displacement, delta CX. So this first one here is how much the structure would move to the right due to P1 and P2 if the redundant was set to 0. This second one here is how much the structure would move to the left if P1 and P2 were not on the structure and the redundant was the only force that we had, and it had a force of -1. Okay, so we have to work out then what the free body diagram is to give us the other remaining reactions. And we should be able to see that if this has a value of -1 here, this is just going to have a value of 1. And these two are going to be 0. Okay, that's just how the method of joints would work for a simple structure like this. And we'd also see that for this structure, these would be the only members taking force. That's why I use this as an example, because it's quite intuitive and it's easy to look through. Once we've got these two values here, we can immediately determine what the actual reaction has to be. And let's think about why we can determine this. So if we determine that due to P1 and P2, when the redundant is equal to 0, the structure moves, let's say, 1 meter to the right. Obviously that's an enormous number, but it's an easy number to think about. So if without the redundant reaction, the structure moves to the right by 1 meter, then that gives us information. That gives us information about how P1 and P2 affect the load here. We're then going to say, okay, let's set the redundant equal to -1. And if, when we determine that, we determine this second displacement to the left is 0.5 meter, then we can sort of think, okay, well, a reaction of 1 Newton only gives us a displacement of 0.5 meter in this direction, whereas P1 and P2 give us 1 meter in this direction. So it follows that for a linearly elastic structure, which we're always going to have, then 1 Newton is half the required value to maintain equilibrium due to P1 and P2. Okay, so it follows that taking that 0.5 Newton, multiplying it by 2, gives us the actual reaction of 2 newtons. Okay, so let's just think about the signs that we'd have involved here. As long as we're maintaining a good sign convention, we'll say we've got y here and we've got our x value here. This one here is going to be a positive value. Okay, positive value because it moves to the right. This one here is going to have a negative value because with a reaction of -1, the structure moves to the left. Okay, so it gives us a minus movement. With these, we simply take this one and divide it by this one, including the sign, and we end up with the redundant reaction. And so what we end up with is our Cx is equal to delta Cx divided by delta Cx. Okay? And we can sort of see this delta Cx is going to be larger if P1 and P2 are going to be bigger, which means that the redundant reaction has to be bigger for a bigger applied load. This one here is just a function of how much 1 Newton does a job here. Okay? So this is the force method, and this is how we determine the redundant reaction on a structure that has 4 reactions. Okay, so this is the force method. We sort of went through it a little bit quickly at the start of term, and I realized maybe we skipped through some of these things, but it's just lost my screen. It's come back. That was weird. It's a simple method, okay, and we use it to enable us to analyze structures that are more complicated than just having 3 reactions. Okay, and the color's gone all funny, but I will just work with this. Okay, so that was the force method. That's a load of squiggles. Let's ignore that. So we can determine the redundant reaction if we've got 4 reactions, and as a consequence we can then use that within the method of joints, so within the free body diagram and the method of joints, to determine the total reactions on a structure, or the total internal forces within a structure. So let me just go back a second actually. Let's have a look at this. So once we've determined this reaction here, we could go back to this original free body diagram and just say, okay, I've also got RCX here, and I'll correct my mistake. I'll say this was RCY because it obviously was in the Y direction. Okay, This then just becomes an applied load on the structure, which means we can determine these three reactions as a function of this one. But this one here is also a function of these two, so if the loading changes, the redundant reaction changes. Okay, and if the redundant reaction changes and the loading has changed, then we need to recalculate these. So we're going to need to do the free body diagram several times over whenever we do this sort of problem. Once we get to this stage, okay, we then say, okay, our reaction, I'm going to put it in red, just meaning that it's a number that we know. Okay, we've then got 3 applied forces to our structure and 3 reactions, by which point we would know all of these. These would just be numbers. Okay, we can then determine these 5 internal forces as a function of all of this loading. And once we've got that, we could also determine how much each of these gets longer or gets smaller. Okay, so we've got all of those. We can see that to do the force method, we're going to need to determine displacements at different nodes. Okay, so for the very simple example we did, we said that actually the displacement of the node to the right, because we were looking at an even simpler example, we just looked at something like this. Okay, so we had a structure like this, and we said actually the displacement of this node to the right is just equal to the extension of this member. Okay, so we can use simple methods for that. If we've got a more complicated looking structure, then we need to think of a better way of solving for displacement. So for that purpose, we said, well, I'm going to introduce work energy methods. So let's say I've got a P here, applied, and if I've got an applied force, let's just write what I'm introducing here, work energy. We said the sum of the external work done is equal to the sum of the internal energy. So if we have one applied load, and on this structure, well, let's even say that we've got, doesn't even matter how many reactions we've got. Let's say we've got 3 reactions on here. The external applied load is P, okay, and this would cause the structure to displace something like this. Okay, I've obviously exaggerated these, but it's some amount here, which we'll call delta X. These two go together to do external work done. And that was equal to UE was 1/2 multiplied by P multiplied by delta X. That was the external work done. And where this method becomes useful is that when we have this applied loading, and if we can get all of the reactions, we can accordingly get all of these internal forces. So we would have F1 through 3. We can equate this external work done with internal work or internal strain energy. Okay, the internal strain energy is going to be equal to, for M members, it's going to be 1/2 multiplied by the force on each member multiplied by the change in length of each member. Okay, so we should be able to see that if we've got a tensile force that's a positive number, we're going to have an extension which is going to be a positive number. So this is always going to be a positive number. Okay, this here, this is always going to be a positive number as well. This is the principle of work energy, and what we're always trying to solve for with this, we're always going to be solving for some external displacement. This is always going to be our unknown. And we very quickly saw that work energy was a cool idea, but if we have a structure that's slightly more complex, then we had, let's say we had P1 and P2, structure that looks like this, we're going to have 2 displacements. We're going to have the structure is going to move a little bit in this direction, delta 1, and it's going to move in this direction as well. So our external work would be, for this structure, UE, would be 1/2 multiplied by P1 multiplied by delta 1 plus P2 multiplied by delta 2. And it would still be equal to the internal strain energy. When we could determine what this is, we just take all of the forces that we could determine in these structures, which we've got from the method of joints, multiply them by the internal, how much each one extends, gets smaller, multiply it by 1/2, add them all together, and we get this thing on the right. So we could do this bit, and we could set up this left bit. P1 and P2 are just things we know. The trouble that we had is that we have two unknowns and one equation. So we can't use work energy, we'll call it naked work energy, to solve this problem on its own. So that's where we introduce this idea of virtual forces. And the principle of virtual work is such a powerful methodology. So we introduced the principle of virtual work. And the most important tenet of the principle of virtual work is that a force does not have to be causing a displacement in order to do work, okay? It does not have to be directly causing a displacement in order to do work. And so what this means is that we can apply virtual forces to a structure. And I went into a bit of detail, and there's a lot of detail in the accompanying notes about virtual forces and the theory behind them. But the basic principle is that if we have a structure, let's say like this, I'm not going to draw that because that would be statically indeterminate. Let's draw a structure like this. And let's say I've got one real force here. Okay, this is some applied loading. And let's say I want to determine the displacement here of this structure. What the principle of virtual forces is that I can apply a virtual force here. Let's call it P star. This is a virtual force. Okay, this virtual force is really small. We don't even really need to care about its value, but we can just say it's 1. Okay. What we can do with this virtual force is that we can say, well, this real force is actually going to cause some movement of the structure. This one doesn't do anything. Okay, it's so small, it doesn't really do anything. But this one does stuff. This one moves the structure, and this one causes a displacement here. Okay, let's call this delta x. And this is a displacement caused by the real force. So what we get is that this force is applied at this node, and this node moves through delta x. So there is virtual work done by this force. And so let's call this U, E, star. This is going to be the virtual force. And because this force was applied prior to the displacements, we actually don't have a half in the formulation of what this external virtual work is. And again, we went through in the notes, we derived it properly, but we can just remember that internal virtual work and external virtual work, we don't have the half in place. So what we would have is P star multiplied, and I'm going to change this to red actually up here. I'm going to change this delta x to red, just to make sure that we know that it's associated with this real loading. So we get this external virtual work, which is going to be a function of this placeholder arbitrary force when moved through this real displacement. And this is only because of the real loading. So we got this set up of the equation. We know that it's got to be equal to something called internal virtual work. Okay? Just like real work, the internal work has to be equal to the external work, or the external energy. So we came up with a formulation for what this would be as well. The internal virtual energy would be equal to an internal virtual force multiplied by a change in length due to the real force. Okay, so this is for a single member. So for the whole structure, we would have ui star is equal to the sum over m members of whatever the internal virtual force is multiplied by whatever the real extension is of this member. And again, remember, this extension is however much each one of these members changes due to this real load. These internal virtual forces here, these are just how this virtual force propagates through the structure. So for each of these members we could calculate, this would be, again, 5 members, we'd have 5 internal virtual forces. We'd also have 5 internal real forces. And it's from these ones here that we can determine the real extension. So this gives us delta L is equal to F multiplied by L on EA. Okay, so this gives us the information about how, though that applied load, P, actually causes this structure to change. These internal virtual forces here just tell us how this node here relates to the internal forces within the rest of the structure. So that's disappeared again. Something going on with my computer today. I'll figure it out later. Okay, so because we can now solve everything here, we can solve for a displacement anywhere on the structure. Okay, so let's think about all of the different things that we have to do when we're solving one of these problems. And I'm going to go through the theory of how we solved the example that we came up with the code for, and then hopefully it will start to click some of those things in place, and maybe just a little bit of a Googling on how do I do X in Python, how do I do Y in Python, how do I do X in MATLAB, Mathematica, will put some of those things into context for you. So let's look at this structure here. In fact, before I go there, let's just see what we did here. Okay, and I'm going to circle this. We can use virtual forces to work out the displacement of any node anywhere on a structure. Okay, so because all we've got to do when we want to find out displacement is put a placeholder virtual force where in the direction that we want to find out a displacement. Say, for example, I've got a big dirty grey truss frame, and we've got, let's say it's statically determinate, and we've got P1, P2, and P3. We've got 3 applied loadings. Let's say I want to find out the displacement of each of these top nodes on this structure. Okay, this means at some point I'm going to have to apply some virtual forces. Let's call them P4 star, P5 star, and P6 star. What this means for this structure is we're going to equate the internal virtual work with the external virtual work 3 different times, and that's going to help us determine these 3 displacements. Okay, because from the external virtual work associated with P4 star, we get the vertical displacement. Okay, same here, same here. So what we have to do is, if we want to determine the displacement of a node, we need to know that at some point we're going to need to apply a virtual force there. And this next bit is maybe the bit that's been catching people out a lot with this. I've tried to maybe get you to think how I think about problems a little bit too quickly. So let's imagine we're going to go into this as a naive undergraduate that just wants to do things, you know, solves an exam paper by question 1, question 2, question 3, question 4, doesn't think about the problem at the top level. then we could do this. We would, in the first instance, we would determine our reactions. We'd do a free body diagram, and we'd work out these three reactions as a function of P1, P2, P1, P2, and P3. We get those real reactions of the structure. We could then get all of the internal virtual forces, so we would have done the free body diagram and the method of joints just as a function of P1, P2, and P3. And let's say these are numbers, 100, 200, 300 newtons. We could have got all of those forces, and then you'd see further down, I've got to work out the displacement of this node here. Okay, so I'm going to apply a virtual force here. And I know that from that virtual force, I need to work out what are the internal virtual forces in the rest of the structure. Which means that for a structure like this, I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 equations to develop as a function of this one thing here, and then the reactions that this one thing here causes. Okay? So you do that, and you'd have gone through it, it's taken 10 minutes, maybe 20 minutes, half an hour to do that. You then read the next question and say, I need the displacement of this node again. Bugger, I didn't realize I'd have to do the method of joints again, free body diagram again. You'd work out 17 new equations to work out the internal forces just as a function of this one. And then again, you'd do it here, and you say, the air would be blue. You'd have to work out all of those internal forces as a function of this one here. So what I've tried to get you guys to think about is, when we're looking at a structure like this, well, let's say, for example, further down in the question problem, it says, what happens if this is replaced with a built-in support? Then that also means that we're going to have to determine a displacement in this direction. So later on in this question, I might have to put something here. Let's just call this F. Well, let's pretend this is node C, FCX. Okay. Then what I've tried to get you guys to think about is that let's do our free body diagram as a function of everything. Let's think about all of the things that we could apply to a structure. Okay, we've got the real forces P1, P2, and P3. And at different points in the structure, I'm going to have to apply P4, P5, and P6. Later on in the problem, when I replace this with a built-in, I'm going to know what the reaction of FCX is because I've done the force method. So I'm going to put FCX there as well. In order to do the force method, I'm going to use a work energy method, which means I'm going to have to apply a virtual force here to work out how much it moves to the right, and then I'm going to have to apply a unit force of -1 to work out how much it moves to the left. Okay, so why not put all of these on the structure? And we only know the numerical values of these at the beginning, but it doesn't matter, okay? Because at the end of the day, that's what algebra is for. Algebra is for determining things as a function of other things when we don't necessarily know what they are. So we've got three reactions, 1, 2, and 3. This is also a reaction, but we're just going to treat it as an applied force. So what we can then do is determine our 1, 2, 3 reactions as a function of everything. And then when we want to determine the real reactions on the structure, when this one here is equal to 0, when FCX is equal to 0, we say, well, we've got 3 equations, which is a function which we're going to call free body diagram, and that's going to be of P1 to P3, which is the real forces, P4 to P6, which is our virtual forces, and then also FCX. Okay, we've got 3 equations that give us all of these. So when we want to know what's going on in the structure, when we've got this set to 0, we set it to 0. And when we are just looking for the real reactions, we set the virtual things to 0. And we then get 3 outputs. You also would have done the same thing to determine the method of joints. So you'd have, again, 17 times equations to determine the internal forces on the structure, and they would be a function of, again, P1 to P3, P4 to P6. You'd have the real reactions, which we'd say 1 to 3. Those are my real reactions, and then you'd also have FCX. So when you want to work out the internal forces on the structure, when we haven't got a reaction here, you set that equal to 0. You'll know what the reactions are here because you would have got them from this method. And when we want to work out, again, for the first bit, when the reaction is equal to 0, no virtual forces, we just set these equal to 0 and we have these things here. Okay? It'd be very difficult to do this by hand because you're going to have to repeatedly do these equations and these calculations over and over and over again. And what I'm trying to get you guys to think about is just to think about at the start of a problem, can I be a bit smarter in front loading my work so I don't have to end up doing multiple iterations of the same thing by hand. Okay, so we've introduced a lot here, and I think this bit, and I will take it on the, I realize that trying to teach you guys the coding at the same time as teaching some of the theory hasn't gone so well. Okay, I expected you guys to be a little bit better at coding. Some of that's my own standards, some of that is a little bit just the way that students are these days, okay, and I sort of accept that. But if you want to be aerospace engineers, you've got to learn to be able to code things up, because that's ultimately how we solve things as modern aerospace engineers. And I say as modern aerospace engineers, I got my degree in 2010 and I had to work out how to write MATLAB scripts to solve things. I didn't have my hand held and walk through it. I had to figure out how to do things. And then, years before that, even just 5 years before that, students were using Fortran to figure out how to do things. Before that, it might have been COBOL, some other language, to figure out how to solve things, maybe BASIC, okay? It's an integral skill of being an engineer, and I can understand I've introduced a lot of Python to try and get you guys to understand this, but this isn't a course in Python, it's just a course in understanding and utilizing physical properties to determine things. And I happen to just, I like Python, but I only learned it a year ago, so it's not like I'm a master that's been doing it for 15 years. Okay, so we're going to go ahead with module 3 soon, and that's very much a computational side of things. So I'm going to try and break down module 3 a little differently. I'm going to try and do a theory lecture and then a coding lecture, theory coding as we go through. So hopefully what we've done today has shed some light on what these different methods are, why we do things. Please let me know where you're struggling with this, what you're grasping, what you're not grasping well, and I will spend time going through them with you. Okay, so I hope you guys are having a wonderful week. I look forward to the review on Wednesday. I will get some lectures recorded for module 3, and I'm going to have a consideration of how the schedule is going to go based on performance so far and what time we have remaining this semester. Okay, have a wonderful week, guys. I will see you soon. Cheers.